Okay, you can start, Lamia.
Good evening, everyone. Good evening, everyone. This is Lamia Benmeziane, computer science from Algeria. With immense exultation, I extend my welcome to dignitaries, guests, opinion leaders, and interested observers. And eventually, thanking you all for joining us today on DevFest22 on its 11th edition on the behalf of GDG Algiers community. Sequined in the night sky, the stars shine, they tell a million of the stories, a story of yours and a story of mine. Yes, indeed, spreading knowledge comes by sharing stories, achievements, and knowledge. That's the only way for a community to grow up and go beyond expectations. Therefore, we are sharing with you today this series of talks led by uniquely remarkable professionals. You really don't want to miss any of these talks. Now, I leave you with Hadjer Benmeziane and the first talk.
Thank you so much, Lamia, for those amazing words. Hello, everyone. I'm Hadjer Benmeziane. I will be your animator today. Without any further ado, I will start with introduction to you, Hadjer Benmeziane. She is a Ph.D. student working on AutoML and hardware and neural architecture researcher with the UPHF and IBM research. Welcome with us, Hajar, and thank you so much for being here today. Her talk is about the story of tiny hardware and deep learning. I will let you with her to explain more.
Okay, thanks a lot. Just like checking if my screen okay, perfect. So thank you very much for the invitation. I'm really glad to be part of DevFest Algiers 2022. And thanks for the introduction. So in this talk, I'm going to tell you the story of tiny hardware and deep learning. So in this story, we're going to discuss these little tiny hardware or embedded devices, embedded and edge devices that you can see on the screen. So the story starts with chapter 1. In this chapter, tiny hardware devices dreams of being used by humans. And so an edge GPU, for example, this little edge GPU dreams to travel the world in an autonomous driving car. A tiny Arduino dreams to help humans in their hospitals and medical urgencies. And others dream to live in their smartphones to get to know humans. So their dream is really to be used by humans. Unfortunately, humans always choose this giant cloud hardware that intensively pollutes the environment, but is very fast. So it's really entertaining for humans to use it. To be able to reach their dream, they need to implement AI algorithms, and more specifically, these neural networks or deep learning models. But as you may know, deep learning models are getting bigger and bigger. So we know about GPT-3, Megatron, that has like 17 billion parameter, 3 billion parameter for GPT-3. So these models are really getting bigger, and they require cloud resources, such as in terms of memory and energy. So tiny ML or tiny hardware called an old friend to the rescue. And this old friend in computer science is optimization. So hardware-aware neural architecture search is an optimization algorithm that automatically searches for the best deep learning architecture. And when I say the best, it is in terms of accuracy, fastness, and also the size of the model should be like really small to be deployed in such devices. And unfortunately, again, execute these optimization algorithms that we call neural architecture search, we are still required to use this giant cloud hardware. So there is much research to be done in order to efficiently search through the search space and find the smallest, fastest, energy efficient, and still accurate model to be deployed in these devices. So let me get you through the most important component in neural architecture search. So the first one is the search space. as you may see here in this slide, the search space is a set of different architectures that we are looking at. So we are trying to search in this search space for the best architecture. And as you may know, in the literature, we have different types of architectures that are used. So we have the convolutional neural networks, such as ResNet, VGG, that you may heard of, the transformers for NLP tasks with a different attention mechanism and combining attention with recurrence, such as BERT, XLNet, etc. And we also now use vision transformers even for computer vision. So we have a different variety of different architectures. And if we construct a search space that contains all these architecture with all the different hyperparameters that we can tune, it would be like impractical to go through this search space and find the best architecture. It would be impossible. Not only impractical, but impossible. So one thing we do is we define specific search spaces. So we can define like a ResNet-like search space where we just tune the ResNet hyperparameter, or we define a vision transformer-like architecture where we take a vision transformer and then we tune the hyperparameter, we tune the number of layers, the number of encoders, the channel output, etc., of each convolution, etc. So this is where we define the search space. It's really important to define an appropriate search space, because this search space will define the ranges of accuracies that we are going to have, the ranges of latencies, etc. Just I think I didn't mention that, but basically the latency is the execution time or the inference execution time of a model. One other thing, okay, so we have this search space, we have a whole search space that we are looking at. And of course, we need an optimization strategy. We need a search algorithm that looks into this search space and tries to find the best architecture. And the most prominent one are evolutionary algorithm and reinforcement learning. So we can use like an evolutionary algorithm that goes around in this search space, trying exploitation and exploration and do some mutation, some crossover, but basically in order to find the best population at the end. Or we can also have like some reinforcement learning controller, and so most of the time it's like an LSTM model, but basically it is trained with the policy that optimizes the accuracy and latency of a model. So we can have like different search algorithms here. And then the most time consuming, of course, in order for the search to explore this search space, it requires to compute the accuracy of each model, the latency of each model, the memory occupation, etc. So we need different evaluation methods. However, you may know that training only one model in like CIFAR-10, which is a basic data set, may take like 2 to 3 hours in a simple GPU. So I'm not talking about a cloud-like GPU. It's still a cloud-like GPU, but not like a really big GPU that allows us to do this in 30 minutes or 1 hour. But in a simple GPU that we can afford, for example, in Colab, it will take like 2 to 3 hours, depending on the number of parameters of your model. So if we do that for a search space of different architectures while exploring, it would take a huge amount of time. So one of the research papers that was published, I think in 2019 or 2018, they talked about like 48 days of running this algorithm and training each architecture, each architecture sampled in the search space, etc. So it is really impractical to evaluate, train all the architecture from scratch each time. So what we need some sort of model that will predict the accuracy of another model. This is kind of meta-learning idea, but this surrogate model will take the model architecture from the search space. Let's say we have 2 convolution, we have 4 layers, we have 1 max pool, 1 dense layer, etc. And then this surrogate model will take this architecture and say, okay, if you have this, then you will have like 93% in CIFAR-10, for example, or you will have like 80% of this is a bad model, this is a good model, etc. This is really cool if we can create these kind of models. And of course, to create these kind of models, we still need to train like a data set. So we still have to train like 1,000 architecture on CFAR10, get their accuracy, extract them, and then train a model that can like predict the accuracy based on the architecture features. It's still time expensive, but not as much as training each architecture sampled by the search algorithm. So we are getting there. It's a good strategy. Another way to evaluate evaluate the accuracy without actually training any model is called zero shot. So what they do is that they take an architecture that is already trained, let's say ResNet 50. We know that ResNet 50 is already trained on CFAR10. It achieves around 95 to 96%. And what we do is that when we take another architecture, we compare the feature map of each layer. We compare if these feature maps or these outputs looks like the output of ResNet 50. And if they look like, so this is, we compute the we compute the correlation between the two. And if they look the same, then we can say that maybe this one will give like 95%. Or maybe this one is really bad. It's really far from ResNet 50. So let's just say it's a bad model and that's it. So these are the most used methods to estimate the accuracy directly. For the latency, we can still use the same methodology like the surrogate model. We can train a predictor that will predict the latency, for example, but we still need to create the data set, of course. We still need to deploy 1,000 architecture around that number and then train our model. We can also like compute the number of convolutions, the number of maybe like max pool, etc. And then we know, like, for example, for the convolution, it takes around 100 nanoseconds. So we can came up with some estimation strategies. Another work that we actually worked on it in my PhD, it's the surrogate model empowered with the learning to rank theory. So the learning to rank theory is used in search engines. So for example, Google, when you query something, when you send a query, you're searching for something, it will internally rank the pages in their data sets. They will rank the pages from the most interesting to the least, according to your query. And then they will, of course, provide you with that list ranked from the top to the least. And what we are doing here is that we use the same strategy, but we are ranking architectures. We say that, okay, we want to know if A is better than B or better than C, etc. So we kind of we kind of use the same strategy that is used in page rankers to rank architectures here. So there are several evaluation methods here. So what I wanted to say in this chapter 2 is that each component of the neural architecture search is like intensively improved throughout different research that architecture search. So if you're interested in this, how can we find the best architecture or the best deep learning model for a given task or a given hardware, then you may notice that some papers like focus on the search space. They try to define a search space that is smaller, that is hardware aware or something like this. Some others focus on the search algorithm. They try to find some optimization strategy that is faster and more efficient. Or some others, they try to find how can we evaluate or how can we estimate the accuracy or the latency better. So you may find like different kind of works there. Okay, now in our story, we will continue our story with a new mutation. Actually, we discovered a new hardware platform paradigm that is called in-memory computing or analog devices. So let's start with what we know. In our computers now, we all use this von Neumann architecture. So we have the processor in one side, the memory in another side, and between both of them, there is a bus that sends and receives the data from the memory. So basically, if the processor wants to execute A plus B, it will receive the first operand, which is A, the second operand, the plus sign, and then do the operation and returns the results to be stored. So all this back and forth between memory and processor, like intensively use it's not really efficient in terms of energy or in terms of latency, because it's really time consuming and it's also energy consuming. So one of the ideas is to mutate the memory and processor within the same components. So this is what we call in-memory computing, where the computations are done in the memory itself. And this is a crossbar. This is like a schema of this memory and how it looks like. You can see that each cell, so the memory is usually like this. The memory is usually an array, and each array, each value, each element of this array will store a variable or will store some sort of value. So it's the same thing here. So we have an array, and each value is stored within a resistance. So this resistance is programmable. In electronic, we can use different devices to create this resistance. But in this presentation, we will just keep it in mind that this is a resistance, and we can put any value in here. And the analog devices, the interesting thing in analog devices is that if I want to store 5, then I will just put in the resistance 5 ohm. I will set the resistance. And if I want to store 100, then I will set the resistance 100. So one question you may have is, okay, but what if I want to store 1,000,000 or 1,050,000 or something like this, a really big number? Can I do it? And can we have the physics to store this kind of number? So I will leave actually this question. If you're interested in that, maybe ask me this question at the end. Okay. So now we're gonna see how can we use this kind of technology or kind of hardware in deep learning. So we have this kind of, let's say we have this convolutional neural network that starts with an image and then executes one convolution, and then we don't care about the following operation like max pool convolution, etc. We don't care. Okay, but let's focus on the first operation, this convolution here. So one thing that we always hear about is that deep learning is full of matrix multiplications. And if we accelerate matrix multiplication, then we are accelerating convolutions. And this matrix multiplication is also used for gaming. So this is why GPUs were really helping in deep learning. But actually, when we read about convolutions, we know that we are applying a certain kernel in a certain feature map, in a certain input. And actually, we are doing some accumulations, and that's it. If we look at it like this, it's not like a matrix multiplication. But actually, in all the frameworks, they use this EM to call implementation, where they transform the input and the kernels into two different matrices, and then it will become like a matrix multiplication. And we transform it like this because we have the hardware that accelerates matrix multiplication. And if you can see, it's bad for memory because we have some redundancy here. 2 is repeated 2 times, 5 is repeated 4 times, etc. So we have some redundancy in the input, but it is good for efficiency and energy efficiency and time and latency. So we are still, we can execute these operations really fast. And in terms of energy, we store everything, we execute fast. So the number of operations is decreased, etc. Okay. So let's imagine we have our convolution. We did the EM to call format. We have the kernel matrix and the input matrix. What we are going to do is that we are going to store the kernel matrix in the memory in our crossbar array. So each resistance here will hold the value of a certain kernel element. And then if we want to execute, if we want to do a multiply accumulation or a vector matrix multiplication, the only thing is the physics rules or laws that we studied in high school. Like the Ohm's law will tell us that the conductance here at this point, I hope you're seeing my mouse, but the conductance here at the first black point here is equal to G1 multiplied by V1. And then the output of this whole line here, or this whole column, is the sum of JK multiplied by VK. And basically using basic like Ohm's law and Fermat's law and basic electronics, electricity laws that we studied, we can achieve like vector matrix multiplication, and it's really fast. It's also in memory because all the results are getting stored within the memory and etc. We don't need to send these resistance values to some sort of processor. Everything is done here, so everything is really efficient. But then one question that we may get from these type of hardware is, then what is the best network for me? We know that during the years, all the architectures that we developed were developed for a certain hardware. So when we started with convolutions, the standard convolution that we know of, GPUs are really good at accelerating these, because with parallelization, with bigger feature maps, etc., we can achieve a really fast convolution. And then we also created this new type of variance of the convolution that is called the depth-wise separable convolution. And it's actually better executed in CPU. It's faster in CPU than in GPU. Because of the way we execute the operations, it breaks the parallelism of the GPU. So it's faster in CPUs than in GPUs. So now, can we like create some architectures or some operations that are suitable for analog devices and in-memory devices? And this is why also we use neural architecture search to automatically create these operations and automatically came up to with a structure of architecture that is suitable for in-memory processing. Okay. It's actually the same, the same components with the same search space, a different search algorithm, an evaluation method. And the interesting thing here is that the evaluation method needs to be tweaked to need to be dependent on these analog devices. And of course, these devices are really novel. They are only like in research now. In the research lab, you can also you cannot find them like commercial or something like this. But the fact that they are still in research, it's because they induce different noises. They have different characteristics that you need to take care of in the search to become an architecture that is not only accurate, not only fast or small or energy efficient, but it's also need to be robust. So some new mutation or new hardware will add some other objectives to our optimization strategy. Okay. The final chapter I wanted to discuss is that, so we talked about neural architecture search in general. What are the different components? We talked about this new mutation with with the analog devices and tiny hardware, and we needed to adjust our neural architecture search for these new hardware. And now we are going to talk about a real-world application. So can we apply neural architecture search not for image classification on CIFAR10? We are never going to use image classification on CIFAR10, but can we really apply it like in image segmentation or dealing with tabular data or medical data? So if we have like an altruistic Arduino, can we use an Arduino in a hospital in order to understand better and to assist radiologists in their work? So some of the challenges of medical AI applications, you may notice that most of them will also happen in different tasks and different domains. But in the medical data, we have these dealing with the medical data has different characteristics. The first one is the NIfTY and DICOM format. So they have different formats for their data. In the DICOM format, if I give you like the result of an MRI, this result will be a file called a DCM. And in this file, you will have the patient's information. You will have the images, of course, but you will also have the radiologist information, the system information. You will have a lot of different information in these files, and you need to analyze these files in order to extract the most important information. You also need to do some data anonymization. This is important. You need to remove all the features that make you find the patient or make you find the radiologist. Data augmentation is also like something that we use in image classification in CFAR10, but can we use all the data augmentation? Like, for example, can I rotate the image, the medical image, completely upside down? I cannot do that because my model needs to know that the lungs are above the stomach. If I rotate it completely, then the stomach is above the lungs, and it's really messing up with my model. Another information that we need to take off, that we need to take care of is the demographic information. So in medical applications, it is really important to make sure that we have all the different patients that are with all the different demographics in our data. So if I, for example, create an application that detects brain tumors, and this application was only, or this model was only trained on man patients, then it won't be deployed in a hospital because we need some sort of data set that cover all the different patients that we are gonna get. Splitting in training and validation, we also do it in every machine learning application. But the interesting thing is when splitting in training, alhamdulillah, when we have a data set in medical, we have way more healthy people than patients that have this disease. So if we're talking about brain tumor, we would have like 100 MRI where the maybe 90 maybe more, 99 MRI where the patient is healthy, and only 1% where the patient is has a brain tumor. So in training, we need to make sure that these values are 50-50, because otherwise our model won't learn what is a brain tumor and where to locate it. But in the validation, we need to make sure that our validation system or our validation set contains the same proportion, so 1% and 99% for the healthy one. This is, I think, a scenario where we always find it in medical AI data, and I cannot think of another situation where we should do the same. For model creation also, it is really important to make sure of the size and efficiency of the model, because all the hospitals are not rich, all the countries are not rich. So we need to make sure that our model can run on a simple CPU and really fast. Because if it doesn't run, then the radiologist will just like turn it off and read the MRI himself. So we need to make sure that this model is really fast and efficient. I want to put a star on interpretability. Here we focus on, it is really important to know why our model, our model chose to select this one as a brain, containing a brain tumor or not. This is really important to understand. It's not my field, but I wanted to emphasize that interpretability is really important in medical AI applications. The last point I want to discuss is the validation plan. So we need, each time we create a model or we train a model, we need to make up a validation plan that defines the set of steps that are required to make sure that our model is still giving good results even after deployment in a hospital or some radiologist lab. So what I did here is I tackled the task of hippocampus segmentation. So hippocampus actually is one complex brain system that is that main role is the main hippocampus is learning and memory. And in patients that have high risk of Alzheimer, we actually try to compute the volume of the hippocampus. And if this volume is decreasing over time, then we say that this patient is at high risk and maybe like having an Alzheimer now. So we need to make sure so the radiologist like make this MRI each time, the brain MRI each time, and segment the hippocampus. By segmenting, I mean like trying to see which pixels are the hippocampus and which are not in each image. And if you can see here in the 3D slicer is actually a radiologist tool. So what they are doing is they take each pixel and they segment, they say, okay, this one is the hippocampus, this one is the hippocampus. And you can see that there is like 3 different dimensions. In the 3 different dimensions, in each dimension, there are 50 images. And they need to do that for 50 images in each dimension manually. It's really huge. So helping them with this task, at least like giving them a starting point, is really important, and will help like will help them be more efficient in their work. So one way we can do that is to build a unit architecture and then train it to do the segmentation. This is already done in the literature, but unfortunately the unit architecture is really big and the inferences takes too long. So one way we can do is to apply neural architecture search and to try and modify the hyperparameter of the unit architecture in order to shrink this model and then get the results that you can see here, still get like a good accuracy, but we can now deploy it on a small Arduino like Uno or Nano. Okay, so I think this is the end of my presentation. I'm just gonna like give you some key takeaways. The first one is, of course, being able to use these tiny hardware that you can see on the slide really help us like overcome some of deep learning challenges, the impact on climate change by changing the efficiency of the models, the need for fast inference. So if we're in an autonomous driving car, we want the car to stop at the right time, not after seeing the person. We want it to stop like really at the right time. And the need for privacy preserving models, because if we use these tiny hardware are actually ours. So they are either in our smartphones or our devices, so we can use them while preserving our privacy. And hardware-aware neural architecture search is methodology to do that. It's not the only one. I focused on hardware-aware neural architecture search because it's the topic of my PhD, but it's not the only one. There are like different compression techniques, pruning, quantization, etc. that also like focus on this. And also we need to go ahead and focus on maybe some accelerators like analog devices and ask ourselves, like, do our models that work on GPUs still work on these new devices, and maybe tackle some AI in healthcare applications that require the use of resource constrained devices. Okay. Thank you for listening.
Actually, thanks to you, because I'm mind blown. Like really, I'm mesmerized with all those informations. You rocked it. It was a very interesting presentation. I've learned a lot, and I guess okay, depending on the comments, all the participants are saying that it was amazing. Thank you so much, Hajar.
No problem. Thank you.
Yes. Now, passing to the questions. So please, everyone, if you have any question, feel free to ask it. Hajar is here to answer, I guess. And before starting with the participant, I would like to come back to the question you said you will answer it in the end about the number of resistance, I guess.
Yeah, exactly.
Okay, please.
Okay, so the idea is that if the resistance actually cannot store any value, like if it's 1 million, then we cannot store 1 million, of course. So what we do is that we use this concept of quantization. We transform the digital value into an analog value. So let's say we can only store like from 0 to 256. If we can only store this, then we will quantize the digital values into this. We will transform them into this range, but we will transform all the values. So if we have like 1 million and 50, then 50 will be closer to 0 and 1 million will be closer to 256, right? So this is why we use like quantization in the analog devices in order to put the weights or store the weight in these devices. And this is really an interesting question, because when we do that, the accuracy actually drops, because we are not really multiplying by 1 million now. We are multiplying by 256. So the accuracy will drop. So this is why we are still dealing with this kind of hardware, trying to overcome their problems and noises and stuff.
Okay, great. Thank you so much for answering. It makes sense now.
No problem.
Okay, so I guess they have no question. They are saying that it was very clear presentation.
Thank you.
Thank you so much again. Okay. I guess we've finished with the first talk then. We thank you so much again, Hajar, for your...
Thank you.
It
Thank you
was
very
amazing,
much.
yes. And willing to see if the combination between the hardware and the deep learning will surface all the challenges you talked about before. Okay, here's a question, if you allow, please. He said, why don't we split them in smaller number than added the result? I guess he's talking.
Why don't we split them? I guess he's talking about the numbers when we put them in the resistance, right?
Yes.
Split them in smaller numbers than the results. Yeah, the fact that the memory itself, like if you can see, like how did we do the operations in the memory? So we cannot really add one resistance plus another. We need to put it in some sort of like, you see that the in-memory compute crossbar follows Ohm's law. So at each cross point, we do like R multiplied by V. What I forgot to mention is that R is not the resistance, is the conductance, because if you go and check Ohm's law, you will see that it's V divided by R.
Right,
but
yes.
R is the conductance, so it's 1 over R. So
Yes.
this is why in the figure it was like V multiplied by R. But basically, we cannot do like addition of two different numbers, of two different numbers within the in-memory computing. We can only do like multiply, add, matrix multiplication, some logical operations like AND, or etc. But we cannot do like some complex operation like dividing a number and then summing them up again, and like it cannot happen.
Yes. Thank you so much. I guess have got the answer he wanted. Okay. So thank you so much, Hazar, for this
No
talk
problem.
and for
I
answering
also
our
forgot to
questions.
mention that my email was there on the slide. I think also my EASY email is still available. So if you have any other question, please ask. It was on the first slide, right? Yeah, I can go back to the first slide.
Okay. Let me screen it.
Yeah.
Okay, great. So guys, here's her contact. Great. Yeah. It was an honor for us to have you, Hajar, again. Yes, thank you so much. And thanks for all the participants for being here. I hope we will see you in our next talk or next events.
Inshallah.
And yes, thank you. Have a good night and thank you.